In the last class, we discussed how one arrives at the Hamilton-Jacobi equation, and we shall quickly review the discussion so that we can proceed further and show how Hamilton-Jacobi equation could be useful. So, we started with a generating function of second type. So, it is the function of the generalized coordinate and generalized momentum and time in general. And for such choice, we have already seen the old momentum, say jth momentum, can be obtained from the generating function using this relation, and also the new coordinates. In addition to that, the new Hamiltonian is simply the old Hamiltonian plus the explicit time derivative of the generating function. And then we mentioned that we would like to choose F2 such that the k vanishes. If k vanishes, then we know it has some immediate application in terms of the new coordinate. The Hamilton's equation would be simply 0, simply because k is 0. So as such, what we get is Pj is nothing but some constant. Let's call it alpha j. And similarly, because k is 0, the other generalized coordinate, the q's, that will also be constant, and we will call them betas. So we see that if we choose F2 carefully, then we can ensure that the new Hamiltonian vanishes. As a result, the new coordinates simply become constant, not explicit function of time. Now, we also have seen that in such cases, instead of calling it F2, the generating function of second type, we can simply say this to be our action variable, because we this is the action functional, because we have seen the total derivative of s, our former F2, that gives us nothing but the Lagrangian. So as a result, S is the familiar action function. So, if that is the case, then you see, as long as new coordinates are concerned, new coordinates are concerned, we can say that k is 0, which means this also is 0, right? Now, what does it mean? It means that we can simply write in terms of q1, qn, and then we have already seen here the p's can be written in terms of the partial derivative of s qj. S and f2 are essentially same. So we can simply write now this equation, as you can see, it has n plus 1 partial derivative, n of them with respect to q's and 1 with respect to time. So if we can solve this equation, then we will get n plus 1 constants, integrals, constants from the integral. So each derivative after integration will give us one constant of integration, and one of this constant will definitely be totally additive, in the sense that the final function s will be like q and then constants, because the p's are constants as we demanded, and it would be a function of time plus some additive constant. So we see that n of these constants are part of S, and one of them is simply an additive constant, let's say n alpha n plus 1. This we will ignore, so simply because it does not change the physics of the problem at all. So our target would be to find S. If we can find S, then we are kind of done with the problem. Now this Hamilton-Jacobi equation, it can be expressed in a somewhat different form, particularly when Hamiltonian is not a function of time. So if the Hamiltonian is not a function of time, then we can write the Hamilton-Jacobi equation as so instead of writing q1 to qn and then derivatives del s q1 to del s qn, we are simply writing qi and del s del qi. So if I write it in full form, then of course it would be both are same. The above one is basically just a notation, a simpler form. Now, if this is the case, then you see, this Hamiltonian is not a function of time, so it must be a constant of motion. If it is constant, then let us suppose we can choose our coordinates such that this would be, let's say, some constant alpha 1. We designate this to be alpha 1. As such, this equation, the above equation, simply has this form, which is easy to integrate. That S would be like, where W is a general function of Q's and we are only integrating the time. So we have alpha 1 t with a negative sign, of course, from this equation, and this W could be any general function of Q's. Okay. So this one we will remember, this is called Hamilton's characteristic function. So as we see that if the Hamiltonian is not a function of time, then the Hamiltonian, which is usually the energy, must be a constant. If it is a constant, then the time integral of S is trivial. We simply integrate this equation, and that gives us minus alpha 1 t and some function of Q's. This function of Q's, we call it Hamilton's characteristic function. Now, when we calculate del S del Qj with respect to some Qj, that must be equal to, after all, alpha 1 is a constant from this equation. So the partial derivative of Qj, that will act only on the W's. If that happens, then the Hamilton-Jacobi equation becomes somewhat simpler. We'll write it here. It becomes H Qi, and then we have seen del S del Qi is essentially del W del Qi. So we write that plus del S del T, which we know is equal to minus alpha, so minus alpha 1, so we can take it to the other side, and this becomes our new equation. New equation, we also call it again Hamilton-Jacobi equation using Hamilton's characteristic function, and there is no time explicitly appearing in this equation. Now this is easy to solve, particularly for 1D cases. So before we proceed further, let us look at a simple example of the application of this equation, and then we will see whether we can formulate something for a more general case. So as always, whenever we were deriving something new, some new technique of doing things, then we were checking out with our familiar example, simple harmonic oscillator. Here too, we take this. So we look at the simple harmonic oscillator problem using Hamilton-Jacobi equation. So what we do is we write down the Hamiltonian. We already know this, where omega is given by root over k by m, and now writing it using the Hamilton's principal function. We start with principal function and then we move to the characteristic function. We already know what to do. We know that P is del S del Q. No subscript because it's only 1D motion. So that means our equation would be 1 by 2m del S del Q. You see, I'm just writing down the Hamiltonian using the new form of P, which is a partial derivative of S with Q, and that's it. Now remember, Hamiltonian is not a function of time here, so this must be a constant. So let's say the Hamiltonian is equal to a constant alpha. In that case, we have and we know that S would be, that's it, the Hamilton's characteristic function and minus alpha t, such that which, as we mentioned above, we can simply substitute that in this equation to get now that's our equation which we need to solve. It's not difficult. We simply rewrite this as we take this and subtract. We can even simplify it a bit, in the sense it would be and then the partial derivative, we take only the positive square root. The negative square root gives an identical solution, except a negative sign, of course. That sign could be fixed from the initial condition, so it's not a big deal. We can start with 1 and then depending on the initial condition, the sign would be automatically determined. Now this we have to integrate. So we can say that we have a problem of this form. This is our Hamilton's characteristic function. So we have not evaluated the integral yet, but it is straightforward. But let's calculate the Hamilton's principal function S, and we remember S is W minus alpha t. So in this case it would be and now we found S, Hamilton's principal function. Then finding out the new coordinate is trivial, and you remember our new coordinate q is constant beta. After all, the moment we wrote Hamilton-Jacobi equation, we assumed that new Hamiltonian is 0, which means the new coordinate is constant, and we decided to call them betas. So this would be equal to the derivative with respect to alpha, of course, and that gives us what? It gives us I just jumped one or two steps that you can easily pause this video and check whether it's correct or not. Alright, we took the derivative with respect to alpha, so you see we did not have to carry out the integral, which we can do now because it's in a more familiar form, in the sense that we bring this t to the left hand side and we find t plus beta to be equal to, after we carry out this integration, this is nothing but sine inverse q m omega square by 2 alpha. That's it. Problem solved. We just found q as a function of time. I mean, to be honest, this should be reversed. So if you do that, then, well, q twice alpha by m omega square, and you have sine of omega t plus. That's basically the solution. And what about p, the momentum? That is straightforward. We already know that this should be del s del q, or if we substitute everything, then we have that's it. Now, I mean, did we calculate actually del s del q? So what we did is, here is s as a function of q's. Of course, you do not directly do this. You integrate it first and then you take the partial derivative. Okay. So this is how you arrive at the p's. Or the now you see the technique is quite powerful, in the sense we had to follow a certain steps which are well defined, in the sense that you construct the Hamilton-Jacobi equation, write down everything in terms of Hamilton's characteristic function, evaluate the Hamilton's characteristic function as an integral. Even if you don't carry out the integration, you can still calculate the Hamilton's principal function, keeping the integral form intact, and from there it is just 2 lines of algebra, okay, maybe a little more, and that gives you your generalized coordinate as a function of time. Now, finding the generalized momentum is either you can use this form, I mean, for that you need to evaluate that integral in S, or what you can do is you identify P to be proportional to q dot with a some suitable coefficients. So I mean, from there, I mean, let's say I write it down in this form, and then put the numbers back, and then eventually you get p to be, you can calculate p. So either way you can do that. I mean, now the way we solve harmonic oscillator problem, this one does not look like very simple. I mean, it looks quite convoluted, in the sense we have complicated integrals, and so I mean, then how does it help? The one big help here is, if you notice, instead of a second order differential equation, you see we have a differential equation of this form, where we have a first order differential but with square. Now this type of problems are called problems quadratures, where you have the square of the first derivative and some function of q's, and these, in principle, if you can carry out the integral, then it is a simple representation of your problem. The problem is essentially solvable if you can carry out the integral. If you cannot, then of course, I mean, one can take the help of numerical integration, but either way, the problem is done, in the sense that at least the integral have been found. Now, for harmonic oscillator, it might be complicated, but there are many complicated set of problems where this routine set of operation is enormously helpful for solving the problem. Otherwise, the differential equations alone, they are complicated to solve, but this particular procedure it is more tractable. So this is why we use this particular method. Another interesting, or rather essential part, which we have not considered yet, is this is essentially a harmonic oscillator problem, and then everything must be in some way connected to the initial condition. But where are the initial conditions? After all, I mean, we found q's and p's. We do have two constraints. One is this beta and the other is this alpha. So we do have two constraints, but then how are they related to the initial condition? Well, that is straightforward, in the sense that say for example, we mentioned that alpha is the total energy. So from initial conditions, suppose initially the momentum was p naught and the position was q naught. Then in terms of p naught and q naught, alpha can be written down in a straightforward manner. And then what about the other coefficient beta? Now beta is again, if you go back and look at this, at t equal to 0 in this equation, in the right hand side, q becomes q naught. So what we have is beta equal to 1 by omega sine inverse q naught, and then root over m omega square by 2 alpha, which gives us essentially again that of course one can get this from the first equation here. So what we found is the two equations, this alpha and beta, they are connected to the initial condition by these relations. Okay. One more interesting point is, remember our our generating function, which is s. S is a function of q and the new momentum, which is alpha in this case, and it's not an explicit it is a function of time, of course. W is not an explicit function of time, but the S is, and this is By definition, it was our new momentum. But then we found that alpha is the energy. I mean, is there any conflict here? I mean, actually, no. The coordinates, I mean, we already discussed the generalized coordinates, they do not have to conform to the existing notion of the, the position and momentum. Not that way. So, by definition, the way we have chosen alpha, and you remember, it appears here. We wrote down Hamilton-Jacobi equation and we demanded this Hamiltonian is not a function of time. If it is not a function of time, then a Hamilton-Jacobi equation can be written in this form. Now only the del S del T, that part, I mean that we would like to integrate, but this not being a function of time, it must be a constant. So we substituted that to be alpha 1. Now you might ask this question, I mean, then why alpha 1? I mean, alpha 1 was reserved for this del S del Q1, its corresponding coordinate. Rather it was more like a new momentum. So why do we choose the new momentum to be energy? The answer is, why not? I mean, there is nothing which is preventing us from choosing a new parameter. You remember, capital P, which is constant, is basically a parameter the way it enters the Hamilton's principal function. So we are not bound by the requirement that we do have to choose a quantity which is like a Cartesian momentum. All we have to choose is some constant which naturally appears in this equation. Now what are these constants? For time independent Hamiltonian, the energy, it is usually energy. The total energy is a constant, it's a natural choice. So in principle, one can always choose the first constant alpha 1 to be the total energy. So its corresponding generalized coordinate, what would it be? I mean, we just found out that, I mean, you remember, we found Q to be constant, and this is a function of small q minus t. Okay, so our new coordinate is constant and it has time as a conjugate part of the total energy. Okay, now see, energy and time, of course, conjugate variables, and they do appear here having this conjugate relationships. I mean, that's perfectly fine. I mean, and we can kind of see, I mean, that how in quantum we will have the Hamiltonian determining the rate of, I mean, the nature of evolution as a function of time. Here too we have, in a very simple way, for a coordinate P being alpha, the new coordinate, new momentum equal to alpha equal to the old energy, corresponding generalized coordinate is simply linear in time. So this energy and time, they appear in canonically conjugate variables. They are canonically conjugate, the energy and time. Okay. The relationship is more deep. I mean, it's deeper than it appears. I mean, it will we will realize this kind of relationship. I mean, we see it in uncertainty principle, just like we have uncertainty relation between generalized coordinate and generalized coordinate and momentum, like delta x, delta p, something like this. Similarly, we do have relations involving the energy and time. The origin is in the construction of the Hamiltonian itself. Now, this is more or less, this completes our discussion on Hamilton-Jacobi equation. We have shown you that how to construct it, and we showed you one example. how it works, and we shall of course know, we have to discuss one more point, and after that it would be officially over. The next point that I would like to discuss is the separation of variables. I mean, particularly if the Hamiltonian is a function of multiple generalized coordinates like q1, q2, q3, then in general, how do we solve the Hamilton-Jacobi equation? It's a one equation. It has partial derivative with respect to q1 and q2 and whatnot. And from there, how do we solve it? That would be the next part we will discuss. Now, as I mentioned, I mean, we will discuss the separation of variables in Hamilton-Jacobi equation. Now, suppose the Hamiltonian is not a function of time. So in that case, we have already seen that Hamiltonian can be written in terms of the generalized coordinates and then Hamilton's principal function, its partial derivative, and I mean, this should be equal to the total energy. Let's still call it alpha. Okay. Now, just an example. So, for example, we have this two harmonic oscillator. I mean, like or rather, let's say we have a harmonic oscillator problem where the harmonic oscillator is oscillating both along x and y. So it's basically a two-dimensional oscillator. For a two-dimensional oscillator, we would be able to write where and kx and ky are spring constants along direction x and y. Now, for such a given Hamiltonian, if we use the above notation and q1 is x and q2 is y, and we have to find, I mean, we have the characteristic functions which we write in terms of q1 and q2. Then if we just simply apply this, what do we get? We'll have I did that I just replaced this in px, and so this would be one part, and then similarly we will have second part, this would be equal to constant alpha. Now, what would be this portion? We expect each of them to be constant. How so? Well, this is basically the energy of the oscillation which only involves q1 or the motion along x, and this is similarly the total energy for the oscillation along y. Now, q1 and q2, they are generalized coordinates x and y, and the motion along x and motion along y are completely separated. For all it matters, when the motion along x is taking place, the motion along y might not have been there. Okay, so, and vice versa. So oscillations taking place along y, and at that time there may not have been any oscillation along x. Either way, you can always say intuitively the motion as it takes place along x, its total energy must be a constant of motion, and it has nothing to do with what is happening along y. Okay. And that is true for the y also. The motion along y, the momentum and the spring energy along y, their sum must be a constant of motion, and it has nothing to do with what is happening to x. So if we have the Hamiltonian written in such a way that the parts of the Hamiltonian are completely separable as additive function in terms of q1, and then in terms of q2, then in terms of q3, and so on and so forth, then it is obvious that for each motion, for each generalized coordinate, that energy must be constant. Remember, we are only talking about Hamiltonian not being a function of time, for which such a demand can be easily made. So suppose we have such cases. Most cases in physics, we have plenty of scleronomic system, particularly happening in any kind of scattering problem, or often we have the planetary motion. In all such cases, we do not have any constraint per se. If we do not have any constraint, and not obviously no constraint means the Cartesian coordinates are good enough, or spherical polar. Either way, we do not have any explicit function of time appearing anywhere in the Hamiltonian, and that means such separations are possible, and then each part will be constant, each energy will be constant. Okay. Now, often such we can't write it this way. For example, it might be possible that Hamiltonian, suppose we have two coordinates q1 and q2. So it might happen that Hamiltonian is a function of q1, and it would be of course a function of del s del q1, and it would be a function of q2 What I mean to say that, look at this previous equation, we had two additive parts, each one had its own energy, and so we can try to equate this part to a constant value and then try to integrate it out. And similarly we can do the same thing with this q2, and then we can compare the expressions and find out a general expression in terms of q1 and q2. That's fine. But then sometimes this kind of separation, a pure addition, may not be possible. For example, suppose we have a hypothetical scenario that we have a harmonic oscillator kind of expression, plus suppose we have q1 times plus some function of q equal to alpha. What then? I mean, it's not a pure addition because the q1 appears here. Then what do you do? Well, first we focus on this part. We say this must be a constant. Why? Well, suppose this function, it does not have to be an addition, it could be some function of q2 and del s q2. That is what we have written here. So suppose instead of this we make it slightly more general, we call it q1 times a function of q2 and del s del q. Okay. In that case, what we can do, we can write that q1 by q2 del s q2. Actually we are writing s, but in this particular problem it is actually Hamilton's characteristic function. So instead of s, w would be a more prudent way of writing it. It really doesn't matter. I mean, our assertions are all correct so far. Now suppose from this equation we take this second term, and this would be equal to and of course we can take the q1 on the other side. And so phi, the left hand side is purely a function of q2 and the right hand side is a function of q1. In that case, again, our previous assertion applies in the sense this function which contains information of the motion along q2 and q1, q2 being good generalized coordinates, they are independent of each other. So whatever happening along q2, that function has nothing to do with q1. So for all it matters, like we said before, there may not be any motion along q1. In that case, this entire right hand side would be constant. And even if it is, it should not essentially influence the motion along q2 simply because the generalized coordinates are, we will see the example very shortly when we try to work with what we call normal mode of small oscillation, but along the generalized coordinates, the motions remain independent of each other. So in that case, this would be a constant. Now, if that is the case, that means if we have in the Hamiltonian a function involving a particular generalized coordinate such that it can be separated out and written in terms of all other coordinates, and then we can demand that this function has to be constant. If we can do that with all the coordinates appearing in the Hamiltonian, that is q1 as well as q2, then each of them will be equal to constant, even if they don't explicitly, they are not equal to the energy along that direction, but they would be equal to one of the constant of motion. It could be angular momentum, which you will be able to verify if you are working with this central force problem in the polar coordinates. Then you will see for the theta coordinate, you will get a function phi involving theta and del w del theta or del s del theta, and that is essentially is equal to a constant which is not the energy along the energy corresponding to theta coordinate, that's more like an angular momentum of the theta coordinate, which we find to be constant. So we have to keep that in mind, that if we have separation of this kind, then too it is a constant. We need basically Hamiltonian, if it is function of multiple coordinates, and if we can rewrite the expression in such a way that we can bring one particular coordinate to one side, leaving everything else on the other, then for that particular coordinate, this function must be a constant, because the other coordinates along them, there may not be any motion at all. Okay. So this is our requirement for the separation. So if these conditions are satisfied, then we can separately equate functions of q's and their partial derivatives of the Hamilton's characteristic function, in which case this we shall replace s by w everywhere in this slide, here or here or here or everywhere. In any case, because this is being a time independent problem, in any case, I mean, this left hand side can in principle be integrated, and similarly for all other coordinate the assertion holds. So finally we will be able to solve, we will be able to find w, and if we find the Hamilton's characteristic function, then we have essentially solved the problem. So this is one big advantage. We shall see more examples later.